Okay, so in this video, we're going to continue our discussion about centripetal force. In the last video, we talked about how centripetal force is the net force required for an object to move in circular motion. It is a force which has to act radially inward. Um, and the two equations we have for centripetal force are we have Fc equals mv squared over r, and m times r omega squared. And of course, both of those equations just come from multiplying the two centripetal acceleration equations by mass, because net force is equal to mass times acceleration. Okay, and so really this is just kind of a circular motion version of Newton's second law. Okay, so in this video, we're going to look at a few more examples with centripetal force, and the first one involves this type of situation. Okay, so this is um, it's called the rotor here. There's lots of names for this, but this is basically a ride you see at carnivals or at Six Flags or something, where basically people get into a tube, um, and the tube spins around, and as the tube is spinning, they drop the floor out, and so people are actually stuck to the wall. And so you can see people here stuck to the wall. Okay, and so we're going to analyze the situation using the concept of centripetal force that we've been talking about. Okay, so let's start with a concept question. Okay, so the question here says, a writer stuck in a barrel of fun, which I don't know if that's a better name than the rotor, but okay. But a writer in a barrel of fun finds herself stuck with her back to the wall. Which diagram correctly shows the forces acting on her? Okay, so look at these possible FBDs. Think about the concepts we've been talking about with regard to centripetal force and see if you can answer this question. Okay, so first of all, it's clear, or hopefully it's clear, that in order for the rider to be stuck, there has to be a net force of 0 in the y direction, right? In other words, the force of gravity on the person has to be balanced out by some other force. Okay, and so you can eliminate B and C just based off of that principle, because there's nothing keeping the rider from falling in these two situations. Okay, now you also have to understand that in order to move in circular motion, you have to have a centripetal force, and the centripetal force, that net force, has to act towards the center of the circle. Okay, and so if you're the person who's stuck and your back is to the wall, the center of the circle is right out in front of you. Okay, the correct answer to this question is A. Okay, and so this horizontal force that provides the centripetal force, and then the other two forces are in balance that stop the rider from falling. Okay, um, B and C are out for reasons we talked about. D is out just because you have to ask yourself, what the heck is that force right there? And then E is out because, again, there has to be a force towards the center of the circle, and the center of the circle is not behind the wall, it's in front of the person. It's like in the center of the barrel of fun. Okay, and so the answer to that question is A. Okay, now building on this concept question, we're going to move on to talking about doing calculations with this type of scenario. And the forces acting in the situation are the force of gravity, the force of static friction, and it's static friction because the person is not falling down. They're not moving up and down, so it's static friction acting up. And the force providing the centripetal force coming straight out of the surface, perpendicular to the surface, is the normal force. And we've kind of seen that situation before when we've done problems like pushing a book up against a wall. And so basically the FBD would look something like this. Now, as we're looking at the next few slides, you'll see R. R, for some reason, is a symbol used to represent normal force by the IB. I don't like using that symbol. I prefer using FN because R makes you think of radius. Okay, but anytime you ever see R in an IB problem, it's really talking about the normal force. That's why we have this equation right here, FF equals mu times R. Just think like that's just the coefficient of friction times the normal force. All right, so this is basically what the FBD looks like. Now, when you're doing circular motion problems, you always want to figure out what force or forces are providing the centripetal force. But in this situation, there's only one force that is radial, and that is the force, the normal force. Okay, so gravity going down, static friction going up. Here it just says FF, but really it's static friction because they're not moving. And then the normal force is providing the centripetal force. Okay, which means that when we go to plug into the centripetal force equation, we have Fc equals mr omega squared, and on the left side we have the sum of the forces in the radial direction because that's what centripetal force is. But if there's only one radial force, then that would just be Fn. Okay, and somebody's going to ask me, is that always the equation for centripetal force? No, it's only in this one specific situation. Okay, in any problem you're doing, you always have to fully analyze the problem from scratch. Okay, so you can't just like remember random equations. You have to go through this thought process, draw an FBD, figure out which force or forces are radial, and then the sum of those forces is going to be equal to the centripetal force. Okay, for this particular setup we have, that is provided by the normal force. Okay, so let's see what this might look like in the context of a calculation question. I also want to remind you, by the way, that the force of static friction is less than or equal to the coefficient of static friction times the normal force. Okay, and so remember the force of static friction can basically match any value necessary to stop motion from happening, but it can't go past the threshold. Okay, and so that threshold, FFS max, is when it's equal to mu s times Fn. And we've seen that before last semester, but I just wanted to refresh your memory about that for the next couple slides. Okay, so let's see what a simple calculation, or a simple, what this concept might be. So the question says the rotor ride is the one which presses you against the walls of the spinning rotor as the floor drops away. The coefficient of static friction between the wall and the 75 kilogram rider is 0.06. If the ride is rotating at an angular velocity of 5.2 radians per second, what is the maximum radius of the rotor can have so the rider doesn't slip? Okay, so we have the FBD drawn already. We write down Newton's second law, aka the centripetal force version of that, because we're dealing with circular motion. And I'm going to write down the equation that has omega in it. Now, I know to do that because they give me angular velocity. All right, so there's two equations for centripetal force. Obviously, you would use the one that has what you need to solve the problem. Okay, so since we're given omega, we should use the equation that has omega in it. Now, the centripetal force, as we've been talking about here, is provided by the normal force. Yeah, is provided by the normal force. Now, the question doesn't ask us to find normal force, it's asking us for the maximum radius that the rotor can have so the rider doesn't slip. So there's a couple things going on here. In order for the rider to not slip, we have to have a condition met. Okay, and that condition we have to have is that the net force in the y direction has to equal 0. In other words, as long as FFS and FG balance each other out, the rider's not going to slip. Now the trick is that FFS has a maximum value, and we just talked about that before. The maximum value that FFS can have is when it is equal to mu s times Fn. Okay, so keep that in mind for just a second. Now I know the mass, 75 kilograms, and so I can find the force of gravity because I know Fg is equal to mg, blah, 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 and so that would be something like negative 750 newtons. And so FFS has to at least be equal to negative 750 newtons. Okay, so we know the force of static friction that is required so that the rider does not slip. All right, now we also have the coefficient of static friction. So let's think about this for just a second. Really, the equation for the force of static friction is FFS is less than or equal to mu s times Fn. All right, so in other words, we know that 750, that is the force of static friction. There's no option about that because that's exactly what's needed to balance out gravity. 750 is less than or equal to mu s, which I actually know mu s because it's given in the problem, right? That's 0.06 times Fn. Now, I don't know Fn, but I do know that it is providing the centripetal force. If I solve this equation right here, then I find that Fn is um, greater than or equal to, I somehow wrote the greater than sign backwards, greater than or equal to 750 divided by 0.06, which is, I'm going to type that into my calculator, 750 divided by 0.06, that's 12,500 newtons. Okay, so in other words, the normal force has to be bigger than that, otherwise the person riding is going to slip, right? Okay, so what that means is that the normal force, aka this, I can set that equal here and solve for R. So R omega is 5.2, so that's 5.2 squared. And then here's my equation. I just need to rearrange this equation and solve for R. And I will just write down the answer because I'm starting to run out of room. I take my 12,500, I divide by 75, I divide by 5.2 squared, and that gives me 6.16 meters. Okay, and so that is the answer to the question. I do want to point out, by the way, that we use the acceleration due to gravity as negative 10 meters per second squared. I think when I show you the answer key, I think they used 9.8 or 9.81 possibly. And so the answer you'll see on the next slide might be slightly off, but that's basically how you would approach the problem. Okay, what I want you to see here is that the concept, basically we're building on concepts we've seen before. Okay, we're still doing second law problems, but we're just adding the extra layer of centripetal force. Okay, so pause there and look at that some more. And I will say, by the way, that this question, the way it's written, on a scale from 1 to 10, this is probably a good 7 or 8 problem. This is not like a basic problem, I would say, because there are quite a few steps you have to do here. But that's a good, solid problem. Okay, so there's the work required. They use 9.81 for G, but basically the answer comes out to be the same. Something interesting that they point out, which I did not mention, is that if you actually plug in values and you plug in into the equation, it actually turns out that you get the same answer regardless of the mass because mass cancels out in the equation. Okay, so interestingly enough, the mass of the rider actually doesn't matter here. The only thing that matters really is the coefficient of friction. Okay, I also want to point out that as the angular velocity increases, right, that means the normal force increases. That means the force of static friction can also increase. Okay, so that's why if the ride goes too slow, then the people are all going to fall. Okay, so it has to be spinning a sufficient number of radians per second in order to stop the people from falling. And that depends on the radius and it depends on the coefficient of friction as well. All right, so just a couple more things to talk about. Here's a concept question. If you weigh yourself at the equator of Earth, would you get a bigger, smaller, or similar value than if you weigh yourself at one of the poles? Okay, so think about that for a second. And this is not a random question. Think about the concepts we've been talking about. Think about what the FBDs would look like if you're at the North Pole versus at the equator. Okay, so see if you can answer this question. Okay, so just to visualize this, if you're standing, let's say you're at the North Pole. Okay, in terms of circular motion, even though the Earth is spinning, if you're at the pole, you're not spinning at all. Okay, and you can think of that like if you think back to the very first slide in this unit, we talked about the 6 paint cans on the wheel that's spinning, and there was a black paint can in the very middle. Okay, and the radius of that black paint can was 0, which basically meant that it wasn't moving at all. And that's basically what your situation would be if you were standing at the poles. So your FBD would just look like this. You have force of gravity going down, normal force going up, and those two are balanced. Okay, no big surprise. If you're at the equator, though, the FBD would look slightly different. And I'm going to draw it sideways so it might look weird. Okay, but you still have the same two forces. You have the normal force coming out from the surface. You have the force of gravity towards the center of the circle. The difference now is that at the equator, you are moving in circular motion, right? Because you're farthest from the center as possible. Okay, so because you have circular motion, you have to have a centripetal force, which means when you add up Fn and Fg has to be bigger than Fn because the centripetal force has to go towards the center of the circle. All right, now gravity can't magically increase, and so the only way for this to be possible is if the normal force on you decreased. Okay, so you actually weigh less um, at the equator than you do at the poles. And you can't see, but I'm using air quotes for weigh. A scale would read a smaller number at the equator than it would at the poles. Okay, because at the poles you're not really moving very much in circular motion. The centripetal force on you is basically 0, whereas at the equator the centripetal force on your body would be at a maximum. Okay, because the net force that's when you add Fn and you subtract when you take Fn and you subtract Fn, I don't know why I keep saying it backwards. When you add up Fg and Fn, the net result, the overall net force has to go towards the center because that's how centripetal force works. Okay, it's a center-seeking force. In a fight between the radially inward force and the radially outward force, the inward one has to win. Okay, and so I just want to talk about one more type of problem that you might see, and that is a problem involving driving. Okay, and so right now we're going to focus on driving a car around a flat curve, or what is called an unbanked curve. Okay, so this is the situation where you're just driving along, the road is completely flat, and I'm going to tell you something, and I want you to just take it as a given. Okay, in that situation, if you drive around a curve and you're moving in circular motion, the centripetal force is provided by the force of static friction between the car's tires and the road. Now, explaining why that is kind of like a pain to do, especially since I can't really see you in person. And so please, if you just take my word for it, that would be awesome. Now, if the road is not flat, then that's different because if the road is banked, what we call a banked road, like you see in NASCAR, like this is what's called a banked curve. In a in a NASCAR track, they intentionally bank it, and so that way there's a component of the normal force that can provide the centripetal force. And so that's why you see NASCAR tracks are kind of angled like that, and it's done intentionally, so there's that extra force adding to the centripetal force that lets those cars move faster. Okay, so we're not going to look at those types of problems right now. We're mainly focused on the flat road situation. Okay, so when you drive around a curve, the centripetal force is provided by the force of static friction. Okay, just take that as a given. Yeah. With that being said, we're going to do one more example, and this is going to be the last type of calculation we're going to see with centripetal force. And then after that, you should be able to do all the problems on your worksheet, hopefully. Okay, so example 5 says a car with a mass of 1,500 kilograms is driving around a rough curved road with a radius of 15 meters. Okay, so the FBD, I'm not going to redraw it because it basically looks like this, and I can't draw better than this. So this is what the FBD looks like. The centripetal force is provided by the force of static friction. Okay, take that as a given, FFS. Now, what that means is that I have Fc equals mv squared over r. I'm using this form of the equation because the question is asking me for the maximum speed that the car can have, and so I'm solving for v in this problem. Okay, we're given the coefficient of static friction is 0.8, and we want to know what the maximum speed of the car is. Now, FC, I can replace that with FFS because that is what is providing the centripetal force. All right, so here's my second law equation. I write down the sum of the forces. There's only one radial force, and now I can start plugging in numbers. However, FFS is less than or equal to mu s times Fn. All right, and we talked about that before. We're very familiar with how static friction works at this point. The normal force I can find in like 10 seconds because in the y direction here, there's only Fn and Fg balancing each other out. Fg would be, if the mass is 1,500 kilograms, Fg would be negative 15,000 newtons, which means that Fn is also 15,000 newtons. And I can do that calculation really quick. Okay, what that means is FFS is less than or equal to 0.8 times 15,000. Okay, so FFS is less than or equal to, let me see what that is. I guess that would be 12,000. All right, so in other words, when I go back over to this equation right here, I cannot have mv squared over r, whatever those numbers are, cannot be bigger than 12,000. Okay, so 12,000 is greater than or equal to mv squared over r. If you try to drive faster than that, if mv squared over r is bigger than that, then you're not going to be able to move in circular motion anymore. And basically what happens is you're going to lose control of your car and you're going to drive off the road and possibly crash or get hurt or something. Okay, so let's finish this calculation. I'll talk more about that. The mass is 1,500. I don't know what v is, but I know the radius is 15. Okay, and so that means that, let's see, 1,500 divided by 15 is 100. I divide both sides by 100, and I get 120 is greater than or equal to v squared. Okay, which means that v has to be less than or equal to, if I take the square root of that number, square root of 120 is 10.95, let's just say 11 meters per second. And that is the answer to this question. Now, what does that mean? That means if you drive less than 11 meters per second, you're fine. If you try to drive faster than that, okay, then that means your speed requirements, your centripetal force requirements are more than the road can possibly give to you, which means that you can no longer move in circular motion, which means you're going to have to move in a straight line. And so if the road is curving and you keep moving in a straight line, you're going to drive off the road. Okay, that's why if you're driving on the highway or sometimes just different streets, sometimes you see when you're driving around a curve, you see these yellow signs telling you to slow down, and it says like slow down to 25 miles per hour or slow down to 30 miles per hour. You see them all the time exiting on the highway. Those signs are specifically designed so that you slow down to a speed where you're not going to drive off the road. Okay, and the civil engineers that designed the road can figure out the calculations for all that based off of the angle of the road and the radius of the curve and the average coefficient of friction, all that stuff. Okay, um, so please adhere to those signs when you're driving your car. Okay. Yeah, if the sign says slow down to 25 miles per hour and you go like 26 miles per hour, does that mean you're going to crash? No, because the civil engineers who design the road understand that people, sometimes sometimes people don't listen to signs, but don't go too much over that for your own safety. Okay, now just in the interest of time, I'm going to leave the last bit of this calculation to you. The question says the same situation now happens on a wet road with a coefficient of static friction of 0.1. Recalculate the maximum speed that the car can have. The calculation is almost exactly the same. The only difference is that you replace the 0.8 with the 0.1. Okay, so I want you to try to do that now, and you can check your answer in just a minute. Okay, so hopefully you got the correct answer, and hopefully I've shown you mathematically that it is way more dangerous to drive fast when the road is wet versus when it's dry. Because there's less friction, there's less centripetal force available from the road, which means that the speed at which you can drive safely is decreased. Okay, and of course it depends on the radius of the road and the car you're driving, all that stuff, but I have used physics to prove that you should slow down when it's icy or wet outside. Okay, so there you go. All right, hopefully you have a better understanding of centripetal force after watching this video. As always, please let me know if you have any questions, and I'll see you guys in the next video.